This is part one of the series Right Triangles and Trigonometry. In this series, as the title suggests, we're going to be talking about right triangles and the relationships within right triangles, including trigonometric functions. So we're going to start this discussion with the basic Pythagorean theorem. The Pythagorean theorem is one of the primary theorems that allows us to establish a relationship between the sides of a right triangle, knowing that in a right triangle, the sides that are adjacent to the right angle are called legs. The side that's opposite the right angle is called the hypotenuse. And there is a relationship between the legs and the hypotenuse. Now, contrary to popular belief, a squared plus b squared equals c squared is not the Pythagorean theorem. It's an equation that can be set up to represent the Pythagorean theorem, but in and of itself, it is not the Pythagorean theorem. The Pythagorean theorem says the sum of the squares of the lengths of the legs of a right triangle is equal to the square of the hypotenuse. Now, in this particular picture, I've established that one leg is b, one leg is labeled a, and the hypotenuse is c. In this particular picture, the Pythagorean theorem can be represented as this leg squared, which is a squared, this leg squared, which is b squared, and this leg squared, this hypotenuse squared, which is c squared. So a squared plus b squared equals c squared. But this is just a representation of the Pythagorean theorem. This is the Pythagorean theorem. Over the years, there have been many different proofs of the Pythagorean theorem, but the one that I'm most partial to is the one made by a 12th century mathematician named Bhaskara. And that's the way we're going to work it in this series. In Bhaskara's original proof, he drew a picture similar to this, and he simply wrote the words "behold" beneath it, as though it were intuitively obvious to even the most intuitive observers that this was a proof that the sum of the squares of the legs equals the square of the hypotenuse. But unfortunately, it's not that intuitively obvious to me, so I'm going to go ahead and work the proof so that you can see where this comes from. I've gone ahead and added some labels in here, and we're labeling each one of the sides of this big square as C. And you'll notice that it's also the hypotenuse of these embedded triangles. So C is the hypotenuse of each one of these embedded triangles and the side length of this big square. The other leg, or the leg of the short leg of each one of these triangles, is labeled A, and A. The longer leg of each one of the triangles is labeled B, and each side then of this smaller square is going to be this whole length minus A. So it's going to be B minus A. So B minus A is the length of this side, B minus A. B minus A is the length of this side, and so on for this side and this side. Now the heart of this proof is to show that the area of this big square is equal to the sum of the areas of the triangles and the smaller square. And that should come up to a relationship that shows the hypotenuse squared equals the sum of the squares of the two legs of one of the triangles. So let's see if we can't reproduce this. So I'm just going to write down what we're shooting for. The area of the big square equals 4 times the area of the triangle plus the area of the small square. Okay, so the area of the big square is obviously length times width. So the area of the big square is C squared. The area of one of these triangles is going to be 1/2, and it doesn't matter which we use for a base. We can say A for the base times height. And we're going to multiply that by 4 because there's 4 of them. 1, 2, 3, 4. Plus the area of this small square, which is going to be b minus a. And it's b minus a times b minus a, so it's b minus a squared. Now let's do a little simplification here. And c squared equals 4 divided by 2 is 2ab plus, now we got to expand this binomial. And the expansion of this is the first term squared. This times 2, so b times negative a times 2, so that's negative 2ab. And this one squared, so negative a squared is, or negative a squared is positive a squared. And so now we simplify this, and you can see that we have a 2ab here and a negative 2ab here. So this cancels this out, and what we're left with is c squared equals b squared plus a squared. So the sum of the squares of the legs, a and b, equals the square of the hypotenuse. And there's your proof of the Pythagorean theorem a la Bhaskara. Before we put this theorem into practice, let's go back to our original picture because there's a couple of other concepts that we need to go through before we actually are able to fully implement this. And the first thing we're going to talk about is the converse of the Pythagorean theorem. Now the Pythagorean theorem tells us what kind of relationship we can expect when we know we have a right triangle. The converse of the Pythagorean theorem is a way for us to tell whether or not a general triangle is a right triangle. So it says if the square of the length of the longest side of a triangle is equal to the sum of the squares of the lengths of the other two sides, then the triangle is right. So that's going to let us take a look at any particular triangle and determine if in fact it's right. We take the two smallest sides, square them, and add them together, and if that equals the square of the longest side, then it's a right triangle. Now, in our solutions of right triangles with the Pythagorean theorem, it's very useful to know about a specific concept in the side lengths of a right triangle, and that is the idea of a Pythagorean triple. And a Pythagorean triple is simply a set of 3 positive integers that satisfies the Pythagorean theorem. So for example, we have 3 very common ones and a 4th that happens sometimes but not as often as the other 3. The most common one is a 3, 4, 5 right triangle. And this is easy to verify if you take a look at what this is. 3 squared plus 4 squared equals 5 squared. 3 squared is 9, 4 squared is 16, 5 squared is 25, 9 plus 16 is 25. So the sum of the squares of these two shorter sides equal the square of the longest side. So this is a right triangle, and that's a Pythagorean triple. So there's 3, 4, 5, 5, 12, 13, 8, 15, 17. These are the 3 most common ones that you're going to encounter. And the reason that it's most common to encounter is because it's very easy to set up right triangle problems using Pythagorean triples. You don't have to do a lot of engineering to generate a working right triangle. It would be a great benefit to you to commit at least the first 3 to memory. And there's a number of ways you can do that. The way I did it is kind of silly, but you can come up with your own way. Is 3, 4, 5 is pretty easy to remember because they're 3 consecutive integers. The 5 is repeated here, and 3 times 4 is 12. 13 is the only number that works with 5 and 12 to satisfy the Pythagorean theorem. Then the last one, 3 plus 5 is 8, and 3 times 5 is 15. And again, 17 is the only number that works with 8 and 15. So that's how I remember it, but you're welcome to pick any method you want. It's not absolutely essential that you memorize these, but it saves a great deal of time, especially on tests. If you're taking a test and you have to do a lot of extra labor to solve a right triangle, where you could take 5 seconds to solve it, it may mean the difference between finishing a test and not finishing a test. So it's definitely to your advantage to at least commit these first 3 to memory. So let's go ahead and start to use these. So here we have a basic right triangle. We have one leg is 6 and one leg is 8. Now we could go ahead and apply the Pythagorean theorem, take this and square it, take this side and square it, add them together, then take the square root of that to find out what this x is. Or we can just, by the off chance that this is a Pythagorean triple, save ourselves a lot of energy. So let's take a look at this. 6 and 8. Is that one of our Pythagorean triples? Well, if we divided this by 2, we would get 3. If we divided this by 2, we'd get 4. That would be 3 and 4, which would make the hypotenuse 5. So this is a 3, 4, 5 right triangle with a scale factor of 2, which brings up an extremely important point, that any multiple of a Pythagorean triple is also a Pythagorean triple. The idea there is that if you have one triangle and you have side lengths that are multiples, so if this is 3 and this side is 6 and this is 4 and this side is 8, then this side is 5 and this side is 10. So you can see that this makes 2 similar right triangles with a scale factor of 2. And that's the idea behind multiples of Pythagorean triples. So any multiple of a Pythagorean triple is also a Pythagorean triple. 8 squared plus 6 squared is going to equal 10 squared. So this value is 3 times 2. This value is 4 times 2. So this value has to be 5 times 2, which is going to be 10. And if we want to verify that, 6 squared plus 8 squared equals x squared. We take the square root of both sides. X equals, this is 36 plus 64 square root. 36 plus 64 is 100. So the square root of 100 is 10. And that's what x is, 10. So let's go ahead and try another example. Here we have one leg that's 8 and another leg that's 12. Well, let's see if this is one of our Pythagorean triples. It's definitely not a multiple of the 3, 4, 5. It could be a 5, 12, 13, but this is not 5, so that's not going to work. And then there's 8, 15, 17. So it's neither of the first 3 Pythagorean triples. So it looks like we're going to be relegated to using the standard old Pythagorean theorem, which is the sum of the squares of the legs equals the square of the hypotenuse. We undo the square by square rooting, square root both sides. So x equals, this is the square root of 64 plus 144, which is the square root of 208. And now, if we want to just get an approximation, we put that into our calculator. But if we actually wanted to find the exact value of this side length, we would have to simplify this radical. And I've done that over here. The square of 208, we start with the first prime number 2. 2 goes in 104 times. 2 goes into that 52 times. 2 into that 26. And 2 into that 13. This is a prime, so we're done. We pull out our pairs. So we have 2 times 2 times the square root of 13, which is 4 square roots of 13, or approximately 14.4. So let's move on to the next example.